past climate change and one I've pretty well just finished at the moment, which is on looking at the future, looking towards the future, trying to see what we can tell about how climate is likely to change in the coming decades, hundreds of years, and even then beyond that into the thousands of years. So the first question, I suppose, is who is this for? And the answer is it's for first-year students who are normally, I teach a course on Introduction to Climate Change for first-year students, but there's enough content if those of you who are teaching maybe more advanced classes could extrapolate or expand or extend the content. The background is that when I first started to try and prepare some of this data, I was thinking back to past classes where I've shown students graphs of climate data, and I realized that, looking back on it, that they haven't really interacted with that data at all. They've just looked at it, hardly assimilated, I think, what was on the screen. I tried passing out some graphs for them to work on, and that was a little bit better. And then I decided it probably was best of all if we could get them to look at the real data, manipulate the data, have it there to play with, learn some graphing skills, which of course are pretty important as well. And so when I started to do that, I discovered it wasn't quite so easy. I think it's got easier the last year or so in the format that people are putting data online. So I decided rather than making them go to the original data, I would try and get it all together, which is what I've done. So the basic material that we're working off, of course, at the moment you should see on your screens my desktop, and you can see the CAMEL website, Climate Adaptation, Mitigation, and E-Learning. And this is the basic form of the exercise, and it's the basic form of all three exercises when you look at them together, where we have a basic table of contents, summary, something about the educational goals, which I think are maybe not as complete as they could be, but it gives some idea of what we're looking at, and of course I'll discuss those more in a moment, and the context with which these questions can be used, and then the descriptions of the individual activities, which I'm going to go through bit by bit, but I'm going to skip down at the moment, excuse me, down to the bottom. One of the things we have here at Richmond at the moment is a lot of pollen, so if you hear my voice croaking a little bit through the Irish accent, then you can forgive me. So if you go all the way down to the bottom, you'll find at the bottom, under just above teaching notes, it says click here to download the recent change modules as PDF, which I recommend that everybody does. The second one, which is to download the spreadsheet associated with the modules, which I'll be talking about in a second. And then finally, to download only the graphs, and I'll explain why we do that in a second. So what you should be seeing now, and somebody needs to yell at me if you're not, is the spreadsheet, an Excel spreadsheet. And the spreadsheet has many different tabs on it. First of all, we have the data tabs. And I just look at one of these as an example. You can see what I have here, and this is some basic, more recent climate data from the various sources, in fact. The second one, then going through the different exercises, this is some of the tree ring data, and beyond that, then looking at some sunspot and so forth. And if we move forward then towards the end of the data in Excel format, these are graphs linked directly to that data. So any changes you make in the data will represent themselves in the graph. Now, when I first ran the program, I gave these spreadsheets to the students directly, and I don't recommend that anymore because they actually are fairly large data sets, and especially for the graphs, it can become a little slow depending on the speed of a student's computer. I mean, it should be fine, but it's maybe not the best, which is why I then, as I said, switched to trying to use some, graphs in PDF format. So now if I can just call this up again, for sharing your desktop, stop sharing. All right. So what I'd like to do now really is just look through the different exercises and hopefully talk for maybe half an hour, 35 minutes, and then field any questions that you have at the end of that. So this is the basic module in PDF format, and you may want to open that from the CAMEL webpage if you don't already have it, and have a look at that. I'm going to spend most of my time, because I'm going to be referring to them, looking at the graphs. You can see here the graphs related to the first exercise. So what I can say about this is it is very much a work in progress. There's a lot still to be done, a lot to be updated. That's the problem, I guess, all of us working in any way with climate data have this problem of things go out of out of date so quickly. So we just look at this exercise. It's one of 8 exercises in total. The first one's on recent climate change. The second one's on the last 2,000 years, looking particularly at tree ring and other proxy data. The third one's will be familiar to everybody, which is the basic healing curve, looking at carbon dioxide since it's been measured in Hawaii over the last just after the International Geophysics year in the 1950s. The role of sunspots is the next one, and then looking at changes in total solar radiation related to sunspot activity using cosmogenic isotopes, so we'll talk about that in a moment. And then, of course, orbital changes, looking at molecular cycles and what molecular cycles can tell us about the future and the past. Coming towards the end, then, looking at the important impact of ocean atmosphere cycles on climate, particularly for students' perspective, trying to discriminate between what's a short-term change in weather, essentially, or natural variation in climate, which we can expect, and long-term variations, the long-term background trend in climate, which is, as we know, largely due to anthropogenic climate change at the moment, warming at the moment. Now, the final exercise is a small exercise looking at net radiative forcing, looking to see, well, okay, what is the overall radiative forcing that which we can measure at the moment, and I compare the overall net with the impact from volcanoes and see, you can see in that case how aerosols from volcanoes have affected climate over that period of time. So particularly this first exercise, and let me just say I'm a little unhappy with this exercise at the moment because the data does need, excuse me, it does need updated. It's a little, and I want to change the source of the data. However, it works as it is. And so in each of these exercises, I'm going to do it this way. I'm going to talk first of all about some key concepts and then answer some of the questions which are posed to give you some idea how I work with the students. First of all, I think as far as this basic temperature data is concerned, is for students to understand that there are multiple data sets. So these ones we have the Goddard Institute data, the research data, the National Climate Data Center data. So it's likely to see that although much of it is drawn from different sources, people interpret this in slightly different ways. It's also to introduce students to the whole idea of global temperature, which isn't intuitively obvious. What does it mean to have global temperature? When the temperature over the world clearly varies from place to place, from time to time, even from moment to moment. So it's a way to introduce students again to the concept of how do we take the global temperature, what is the meaning of the global temperature, how do we interpret that in terms of telling us something about the present and probable future of climate change. It's also a way to introduce the whole concept of anomalies, not necessarily intuitive to students as well. What is a climate anomaly? Well, I guess we can explain that fairly quickly, but then we have to get down to explaining, well, different people use different bases for those anomalies, and then so why do they use a different base for each anomaly? What's the impact of that on the data? When we look at it, how does it change the data? That brings in again the concept of running means. When we look at this, when they're looking at the actual graphs with the original data on those graphs, they can work out, well, let's redo this graph. Let's run a 10-year running mean, or a 5-year running mean, or a 2-year running mean, or 1 year, just to see how that affects the noise in the data compared to the signal. And they can work out for themselves what appears to be pick out what they're actually looking for. And this one as well, they can see land-ocean differences, which is looking at the anomalies. Clearly, the anomalies are slightly less over the oceans because of the heat capacity of the oceans being so large compared to the heat capacity of the land. And also, it's possible to bring something out of this, perhaps. I think just looking at it, we want to say something to emphasize with the students the fact that the trends are the same over both the oceans and the land. And of course, I'm assuming everybody's familiar with the basic trends that we're looking at, where we have very little warming, in fact some cooling leading up to the turn of the last century, then substantial amount of warming up until the 1940s, then a period of stasis or perhaps slight cooling up until the late 1970s, and then a warming trend through to really the current day, although there has been a slight decrease in warming over the last 10 years, but certainly not a stop to global warming. So that's the basic idea of that first exercise and get them to observe the trends, get them to understand the different organizations involved, get them to look at the patterns, get them to look at the rate of changes. I think a theme that runs through this is to ask students to consider the rate of change, because so much to do with the issues of climate change is not so much that the temperature is changing, but it's the rate at which the temperature is changing. And of course, we want to talk about the spikes, and why do we have spikes in temperature. I'm not sure if you can see my mouse, I hope you can, but of course we have the large El Nino spikes at different times, and the corresponding La Nina troughs, which we can talk about and see how that's superimposed on climate. And I usually finish this exercise talking to students and asking them to draw a graph of what would a graph of the tide coming in look like. And because it would perhaps look something like this, where each spike is an individual wave coming in, and gradually, of course, the tide comes in. But if you stand on the seashore and wait for just a few minutes, you won't necessarily realize that the tide is coming in or coming out. Some large waves will come in, some small waves will come in, equivalent to La Ninas and El Ninos, or other way around. But if you wait long enough, as it is with climate, you'll see the underlying trend appearing, the underlying impact of climate coming in. So all those things I try and draw into that first exercise. The second exercise, excuse me, here we go. Then looks at the climate record over the last 2,000 years. Key concepts here, I think, that I try and bring out for the students are, again, that there are multiple proxies. And so much of the controversy about climate change for a while, and it's still going on, focuses on the so-called inadequacies of tree ring data. However, of course, tree rings are only one source of the data. There are many other sources of data. And even if we take tree rings out of the equation, we still see the same underlying trends. So that was, I guess, one of the major themes for this particular exercise. And then also to address the whole issue of the medieval warm period, which was still much beloved by many climate skeptics, and the Little Ice Age, pointing out that, yes, they were real events, at least in the Northern Hemisphere, at least where most people were reporting at the time in Northwestern Europe and parts of the United States. And we can see these events. The upper graph here is, of course, a graph without the tree ring data, and tends to emphasize, which is mostly Northern Hemisphere data, emphasizes the medieval warm period or climate anomaly, whatever we want to call it, but also shows, I think, very clearly how the warming we're experiencing today, even if we take out the tree ring data, which includes some southern hemisphere data, which, since the medieval climate anomaly does not appear to have been so prevalent in the southern hemisphere, does tend to reduce the amplitude of that anomaly. But even if we ignore that, students can still see that our warming today is unprecedented within the period of time that we can look at this proxy data. And of course, for comparison, the graph below is Jones-Mann data from 2004, where we see a more typical hockey stick kind of profile coming out, which does show the Little Ice Age, and but less pronounced medieval warming. And of course, the political, social repercussions of that particular factor are still going on, even in Virginia, as I speak. So the specific questions about that, again, just relate to trying to draw students' attention to the differences between these two different graphs, and how, even if we accept those differences, that the same underlying data comes out. I also ask students here to think about the different meanings of the anomalies, because Lowell doesn't use an anomaly as Jones and Mann, just look at the 1961 to 90 average as a base for their anomaly. And Lowell uses a different statistical method, a valid statistical method, but a different one. And so I ask them to do this. And one of the things I recommend, it depends on the level of the students, is to get them to go, of course, here to the original papers. They're accessible, they're free online. I don't think they're behind a firewall or a paywall, whatever. These are just Googleable, and it's always good, of course, to get students to look at primary sources of information to interpret some of these data. So some of these questions aren't intuitively obvious from the data. Sometimes they need to go chase outside the data to find it somewhere else. Exercise 3 is, of course, should be familiar to everybody, I guess. It's the carbon dioxide data from Mauna Loa on Hawaii. And here is just clearly looking at the anthropogenic carbon dioxide. One of the things I like to bring out about this is to look at the impact of seasonal variation. It's small, of course. It's this sawtooth pattern with the, I think as Al Gore said in his infamous movie, the Earth breathing in and breathing out. But in fact, it's the Northern Hemisphere breathing in and breathing out. And that's just an interesting point to see as students can correlate this, to see that the levels of carbon dioxide correspond to Northern Hemisphere summers and winters, because most land is concentrated in the Northern Hemisphere, so the impact is greatest in the Northern Hemisphere on global levels of carbon dioxide. I also ask students to use this to project into the future, to say, okay, we've got a fairly consistent trend here, which we can see, say, from 1997 through to the present day. And if we continue burning greenhouse gases and adding greenhouse gases, carbon dioxide particularly in this case, to the atmosphere over the next 10, 20, 40, 50 years, what is the level likely to be? And then later in the courses that I work with, we relate that to increased radiative forcing and the likely impact on global temperature. And of course, the bottom line is they can look at the increase in carbon dioxide from the beginning of the record in late 1950s through to the current day, and just see exactly how much carbon dioxide, over 30% increase in carbon dioxide added to the atmosphere. And that opens a conversation with students. Often we've heard some climate skeptics talk about the carbon cycle and how much carbon is in the world, how much is cycled each year between the oceans and the atmosphere. And that gives us the chance to talk about equilibrium, how the level of carbon dioxide in the atmosphere was pretty stable for a long period of time, pre-industrial times, until the current time. And also to discuss the aspect of carbon dioxide being released from the ocean as the oceans warm as well. How much is anthropogenic, how much of the carbon dioxide in the atmosphere is maybe released from the oceans, and then we have a chance to talk about carbon isotopes and the isotope data, which allows us to see that, of course, much of this is coming from biogenic sources on land, trees, and other burning of fossil fuels as well. All right, let's move on to exercise 4. And we're looking at some sunspot data. This is sunspot data from as long as we have it. So as you know, the sunspot cycles are numbered, so you can count them yourself through 23, 24 into the current cycle that we're in at the moment. So as to introduce students to the idea of the sun does go through natural variations. That sunspots are related to these natural variations. In fact, although in some ways it's counterintuitive for some students that when the sun looks a little darker in places, it's actually radiating more intensely. It's a good way to discuss that. So sunspots are related to slight increases in the intensity of solar radiation. They can see that not each sunspot cycle has the same intensity. And so some sunspot cycles, that's a hard one to say, produce a different impact on climate. They can see the maxima and the minima, and just again, if my cursor works, we can see, of course, around the time of the Little Ice Age, we had a pronounced minimum, and we can see the climate, again, the number of sunspot intensity increasing through the 50s, and incidentally, there wasn't much of a change in temperature over that time. And then see how we're actually looking at a slight decrease at the moment going through the current cycles, in fact, into quite a prolonged minimum leading up to this rather low intensity cycle that we're in at the moment. So it's a way to discuss the impact of sunspots on those cycles. We can also bring out, of course, the difference. The 11-year cycle is easily read off, maybe not so much of this graph, though it is, but off the original data itself. And I've just made some notes here. I don't think I need to cover it, just thinking about our time, but we can look at different periods of time and relate that back to the climate data that we have, the temperature data that we have, to see, where does the relationship match, and it does match in some places, and where does the relationship seem to fall apart. It's a good way to start introducing students to the question, well, what is influencing climate? Sun clearly is the most obvious thing that could influence climate, so what has the sun been doing, and how can we relate that to what we're seeing happening in the world today. So I think that's quite a nice little exercise. Students seem to enjoy that one. If we go on to exercise 5, it's extending this really further back in time. So the key concepts that I try and introduce in this one, and we're looking at sunspot numbers first of all from the paper by Solanke et al. Going back 12,000, well not quite, over 11,000 years in the past. And then at the bottom graph looking at more modern times. Let me just say that if I could come down to here again, this is an error. It's not the medieval maximum here, 1,500 years ago. Of course, it should be through the medieval times around here, so we can just ignore this one. But it's sunspot activity over the last 2,000 years, and looking particularly, of course, we can see I've marked the major minima which occurred during that time. So I'll come back to that. It's also a way to talk about cosmogenic isotopes and how they can be used as climate proxies, particularly carbon-14 and beryllium as well. And thinking more in terms of large-scale changes in trends in total solar irradiation, which have been taking place related to sunspots over a long period of time. And there's a lot we could talk about here in this original graph. Of course, I guess the main questions I ask try to get students to understand, well, why is this so noisy back here? Of course, part of the reason there is we're looking at data precision and accuracy. It's a way to discuss, well, as the further we go back in time, the less precise and less accurate also our data becomes, and how do we interpret that effectively? How do we deal with that imprecision effectively in our analysis of climate data? I usually introduce Milankovitch cycles at this period of time again and ask them, because we have done this, and there is an exercise later, we'll come back to it again. What could this be related to? What would the impact of the Milankovitch cycles have been at this time? So yeah, there are a number of questions. Basically, we're looking at changes which take place. And of course, the major point I try and bring out is over the last 5,000 years, we've seen a slight decrease in the intensity of sunspots until, and it is interesting and it is important, the way that sunspot activity has increased, solar irradiation has increased in intensity recently, and probably was responsible for some, if not most, of the global changes in temperature that we saw taking place in the early part of the last century. Of course, the critical thing here to bring out, as we will later on, is that, well, that really doesn't work for the last, since the 1980s and onwards, because solar irradiation has been generally decreasing in terms of sunspot intensity, but the temperature has just kept on rising up the whole time. So, but nevertheless, it is important to point this out to students, but also to compare it to what the intensity, sunspot intensity has been going back at least 11,000 years or so. Although again, I'm just giving a warning that this far back, I'm sure you all know this, it really is not quite as accurate as it should be. Then for the second part, looking at the last 2,000 years, again, it's just trying to relate to thinking about the medieval climate anomaly and the little ice age. They've looked at that temperature data, trying to relate it to what they see here, trying to see, can they spot the different minima and what impact those minima might have had, looking at in the number of years or the present on the right-hand side, working backwards. And I suppose if I've made an error, I made many errors, but one error in this data exercise is that the scales aren't always consistent. Sometimes time runs from left to right, and sometimes from right to left. And that does confuse students, and I apologize for that. In a later iteration, I'll try and change that to make sure everything points the same way, and some of the scales are maybe a little clearer. So moving on to exercise 6. That's 7. Let's go back to 6. There we go. And here I try and introduce students to the concept of again, Milankovitch cyclicity. So during this time, we talk about different aspects of Milankovitch cyclicity, the precession of the equinoxes, eccentricity of the Earth, so with the obliquity of the Earth's axis, and how that all affects climate over long periods of time. The data clearly is looking at solar insolation at 65 degrees north, and so that begs the question from students, well, why 65 degrees north? What's so special about 65 degrees north as far as solar insolation is concerned? And then it gives us an opportunity to talk about the issue of, well, what makes an ice sheet grow? Is it the amount of snow that falls in the winter, or is it the amount that melts in the spring? The analysis suggests that it's the warmer springs, it's the amount that melts in the spring and following summers obviously determines, not obviously, but determines how much ice accumulation takes place. And when we look at this, of course, and the main thing is to look at over the last 10,000 years or so, we've been seeing the amount of solar radiation at 65 degrees north decreasing as obliquity has changed. And that will eventually change, of course, again. But it's further evidence that if we were expecting the climate to change naturally, what is natural climate change as opposed to anthropogenic climate change, this signal and signal from the sun, which we looked at before over the last 20 or so years, suggests that we should be cooling. There's no reason that we can see it as far as solar irradiation at the moment, and certainly not in terms of the larger, broader, more important in some ways, the Milankovitch cyclicity. There's no reason that why the world should be warming. This can be a fairly quantitative exercise depending what you want to do with that original data, but I do like to point out to students that the differences in the levels of forcing, and of course we have to talk about climate forcing in the first place, but the difference between the maximum and minimum we're looking at here in 65 degrees north is as much as 10 watts per square meter or more, compared to just 1 to 2 watts per square meter for the differences with sunspots. So it's an order of magnitude, or I know an order of magnitude greater impact on solar irradiation at 65 degrees north because of the Milankovitch cyclicity as opposed to solar radiation. So, and then moving on again still to exercise 7, which is a little busy. And if I could just go back to the analogy of the waves again, if we looked at that initial climate data and said it was a bit like looking at the waves coming in the shore, then these are the waves as opposed to the tide. The anthropogenic climate change that we see taking place, the warming we see taking place, is all related to the tide coming in. These cycles are related to the individual waves, some big, some small. And so at the top I have to remind them by this stage, they've probably forgotten it, what the basic pattern of temperature change has been over the last 100 years or so. And then I introduce data from a number of different natural cycles. The PDO is the Pacific Decadal Oscillation. Of course, is the ENSO, the El Nino Southern Oscillation Index. Down at the bottom you have the American Atlantic Multi-Decadal Oscillation, and of course the North Atlantic Oscillation as well. And so the exercises that I ask the students to do are largely just looking through this and trying to see how the data relates to the temperature data that we're looking at. So let's see if I go back up here again. Now, one of the things to notice, I've tried to make sure these are all on the same scale, so students should be able to relate one graph back to the other graph as they're looking through works in the PDF and also back on the original spreadsheet as well. So we can talk about the PDO. It has a 20 or 30 year cyclicity. We can see looking here again around 1950, there does seem to be some relationship between short-term changes. There is a relationship between short-term changes in global temperature and the cyclicity we see in the Pacific Decadal Oscillation, but it doesn't explain the underlying trend. Again, it's one of the common themes of climate skeptics. If you just do a search on the web of what the impact of the PDO is on temperature changes, you'll see this a lot of the time. They believe that, or suggest that it's driving climate change, and it does over the short term, but not on the long term. It's the same when we come to look at the El Nino Southern Oscillation and look again at that impact on climate. We see clearly it has an impact on climate. This little graph on the right-hand side I'm using just to illustrate to students the fact that there is some similarity between the El Nino Southern Oscillation and the Pacific Decadal Oscillation in terms of temperature distribution around the globe, although the El Nino is much more intense and may, I guess still out there, have some role in driving the PDO on a larger scale. It sort of comes and goes. And the Atlantic multi-decadal oscillation we have here, again, they see it has very little impact apparently. If again, let's just roll back up again and compare it to the temperature changes we see globally. There's very little relationship we can see here between the Atlantic multi-decadal oscillation and global temperature, but there is a reasonable relationship between Atlantic multi-decadal oscillation and the frequency of hurricanes in the North Atlantic, which of course are important. One of the big questions is what would happen to hurricane frequency and hurricane intensity as a consequence of anthropogenic warming? And the answer is, well, intensity almost certainly will increase. It's intuitive, although there's some counter-arguments, but most what I've been reading suggests that the intensity is likely to increase, but the frequency is less certain. It could be that the frequency is driven so much at the moment, at least in the Atlantic, by the Atlantic multi-decadal oscillation, that any changes related to anthropogenic global warming may be hard to pick out from the natural amplitude of the swings and change that we see related to the changes in ocean temperature, natural changes in ocean temperature in the Atlantic. And then finally, the North Atlantic Oscillation Index, which is so noisy, of course, is of interest from year to year as how it affects our climate. Of course, this winter is, in Virginia at least, is so different from what we had last winter. I don't think we've had more than 2 frosts, and last winter seemed to be continual frost. Here this winter we've had hardly any snow. Last winter, of course, we had so much snow. So it's, again, the primary reason for showing this selection of data is to make them think about the waves in our tidal analogy. Natural oscillations take place. Climate scientists understand natural oscillations. There's more we've got to learn, right? But we understand a lot about natural oscillations. They're there. We know they're there. And it also shows us, or I use this to point out to students, this is why we don't really think about establishing has global climate changed over 10 years. It means nothing to ask about temperature change over 10 years because these natural cycles can dampen that change or indeed accentuate that change over any 10-year period. We need to look at 13 years, even ideally, of course, longer than 30 years, to start to see clearly the overlying, to extract that underlying trend in anthropogenic climate temperature change from the natural changes which occur because of natural cycles in Earth's climate. And then finally, on to the last exercise. And this I just thought was an interesting exercise to put up at the end. It's not particularly in-depth in any way. I just, again, looked at the different levels of forcing involved and the overall climate forcing and the superposed on the temperature data. And of course, we can see some clear correlation between the temperature data and the mean net radiative forcing. So it's probably best to go down to here and look at this lower diagram first of all, the mean net forcing relative to 1880, where most of these peaks we see here relate to volcanic eruptions. We've Mount Pinatubo here, which cooled the Earth for around 1 degree for up to 5 years. El Chichon in Mexico, and just that was 1982, I think. And Mount St. Helens doesn't really appear in the climate data. And others, the names of which, frankly, I forget at the moment, going back in time. I actually come back to this question of volcanic activity in the third exercise in a lot more detail, analyzing volcanic activity in the past and its impact on climate. I just think just because it's a really interesting thing to predict the future as well, is if we look to the future climate change, is volcanic activity likely to have an impact? What are the chances that we'll see an increase in volcanic activity in the future? Okay, so this is a simple analysis for students to look to see how the climate forcing has changed. We can, of course, factor in the anthropogenic component, the greenhouse gas warming, aerosols factored in, and particularly this aerosol effect from volcanic activity, which is the primary lesson I try to draw from this diagram, is the impact of volcanoes on Earth's climate. And that really is the last exercise. I'm just aware that I want to leave time. Hopefully some of you have some questions, constructive criticisms, which of course I'm very happy to hear as well. So I'll leave it back to Jenny to see where we go from here. Thank you.
Yes, thank you, David. That was excellent. We do have one hand up from Tim Forsman. Tim, you are off mute, and you may voice your question, please.
Excellent. You can hear me now?
Yes.
I can, sure.
Wonderful. brilliant presentation, and thank both Jenny for hosting and of course David for your excellent work. My quick two questions was I didn't quite catch again the percentage difference between the sunspots and the Milankovitch when you talked about, because a lot of people try to put those as equal, but you said it, but I didn't quite catch the percentage difference.
I think it's around, what my notes here tell me 10 watts per square meter for what we've seen recently in the Milankovitch cyclicity. It's possible within, I'm looking at the phone as opposed to the video, it's possible within the, if we look at eccentricity and the impact of eccentricity in orbit, on the Earth's orbit as well, my memory says we can get up to 30 watts per square meter difference there, so it really is a lot more than we're seeing from sunspot cycle. The final module of these three modules actually focuses so much on Milankovitch cyclicity and the details of that. That I don't think is live yet, but it's about to go live. And if you're interested in that, I recommend that to you. It's designed to take students through in some detail Milankovitch cyclicity, look at climate forcing in some detail.
Oh, that's good. I've tended to just say it accounts for no more than about 1.5% in general, but I'm going to have to go back. I want to be a little more precise in my own, and that's why which you showed reminded me of that. The other one, quick question, was, and then you started getting to it right at the end, Pinatubo. I've shown Pinatubo. I have a recent college textbook, Visualizing Physical Geography by Wiley. Highly recommend it. It supports everything you said. And in it, I show on the Keeling curve the dates of Pinatubo and the others. And as you could see, you don't even see it in the chart. But so juxtaposing those two really gets people to think about the issue of the volcanic ashes and then extrapolate to geoengineering concepts as well. So I found it to be, by putting them together, which you didn't, and that's why I was going to ask you, had you put the two on top of each other, that it really does, the carbon dioxide and the volcanic timing gets them to ask some really good questions. And again, I thank you. Those were my only two questions. Brilliant work.
Oh, that's a great idea. I mean, I haven't done that, but it is a great idea. And I suppose that because I've uploaded the raw data here as well, it's something you could ask students to do as a graphing exercise. I mean, I can certainly do it in a later exercise, but all the data is there. The students could do it themselves. And again, it depends on the level that students are working at when they come to this data, but I do like to get students to work with spreadsheets. I'm surprised these days really at how little some students have learned about spreadsheets, even science students, on the liberal arts college, but still we have science students, and they still have a lot to learn. So I use that as a sort of added value aspect of this. So those are really good points. Thank you, Tim.
You bet.
Any other questions?
Yes, this is Lori Ruberg. I had a question.
Okay, go ahead, please.
I'm looking at the graphs that you posted and that are still live on the WebEx screen, the net forcing and CRU global temperature, and the mean net forcing relative to 1880.
Yes. And
what I wanted to ask is, there are several terms and acronyms that it's hard for me to interpret out of context, and I was wondering if you could just verbally explain the title, Net Forcing and CRU Global Temperatures, if you could caption that for me.
Actually, you make a very good point. One of the problems of teaching this and writing about this is that we get so embedded in our own terminology that we forget that it's unfamiliar to most people in the world, and especially our students. So that's a very good point. The CRU is just the Climate Research Unit in East Anglia, who produced I just used their data to plot a basic temperature curve. The net forcing is looking at when you consider basically the amount of energy coming into the Earth's upper part of the Earth's atmosphere and the amount of energy leaving the upper part of the Earth's atmosphere, and where the imbalance occurs between those two is where we find there is the climate forcing comes from. That's what either heats or, if there's a negative imbalance, cools our climate. So it's really the difference between the amount of energy coming into the atmosphere and the amount of energy leaving the atmosphere. And when we have, of course, the major volcanic eruptions and aerosols in the upper atmosphere, that reflects more of the sun's radiation, and so we see a reduction in the amount of forcing, and it becomes negative forcing, basically. It's cooling the Earth because the Earth is losing more temperature than it's actually gaining. Does that answer your question?
Yes. I was also wondering, are you getting the data then from satellites because it's in the upper atmosphere?
That's a very good question. There is climate data from the upper atmosphere, which looks at the difference between, over a period of time, at the amount of radiation leaving the Earth's atmosphere. The problem with climate data, trying to measure climate forcing directly from satellite, as I understand it, and that's not my particular area of expertise, but what I've read, is that it's on the margins of the sensitivity of the instruments. And so what appears is consistent with our other observations, appears to tell us about the same imbalance of just a couple of watts per square meter. But I don't believe that most of this, I think, is not from direct satellite measurement. And that's a good question. Frankly, I would need to go back and check that, but from my memory, this is not from that.
Oh, then what would it be from?
Oh, there would be modeling, I suppose. It's just, again, knowing what carbon dioxide emissions are, knowing what aerosols levels were.
Okay.
This is largely coming from climate and direct, and some of it perhaps from other direct observations from satellite. But in terms of actually measuring I'm trying to think very carefully here, the directly measuring from satellite, the imbalance has been done, can be done, but it's at the limit of instrumentation. And if there's somebody else on the line who knows more about that one than I do, please, bark in here and give us all the, what you know. Tell us the answer if it's different from what I've been saying. Anything else, Laura?
You can't hear me, can you?
That's very helpful. Thank you very much.
You're welcome.
Hello, Jenny.
Yes. Is there anyone else that would like to ask a question?
Can you hear me, Jenny?
Yes.
Oh, yeah. I was going to say that on that last issue, it's a combination of weather balloons and satellite monitoring and scanning from the surface, and it is extremely tricky, and it was controversial, raised a lot of controversy for quite a few years with the temperature between the ground and the upper atmosphere, but the monitoring. So it's done again extremely complex, and it's a combination of measurements between the weather balloons and satellites and ground measurements, pointing instruments up.
Okay, thank you.
Okay, guys. Jackie keeps trying to get out where the doggies are.
Okay. Anyone else? Everyone is off mute now, and you may ask your questions freely. Go ahead.
Fantastic. Thank you so much. David, can you hear me?
Yes, I can hear you fine. Thank you.
I have two questions. The first is about in the plots you showed, it was I downloaded the PDF while you were giving the presentation. It has the recent climate change by Lowell 2007 and Jones-Mann 2004.
Yes.
My first question is, what's the difference? I haven't looked at either of these papers, but what's the difference in those data sets in terms of how the data was collected? What's the main difference between the two?
As I understand it, I mean, I've read both papers, the main difference is that Lowell excludes tree rings. It was around the time that tree rings were particularly controversial. And I guess he was trying to show that, well, I was about to suggest maybe there was some reason why he did this apart from the scientific reason. I don't think there was. It did, though, revive the medieval climate anomaly, which was to the delight of some climate skeptics, who still missed the point that even even if you did that, it was still much warmer now than it was back in the medieval times in Northern Europe and northeastern United States. And the man data, of course, is just multiple proxy data from all including tree rings from all different sources. Also, I think the man data, Jones and man data, includes Southern Hemisphere data, which I don't think Lowell included in his as well. And as I understand it, as more Southern Hemisphere data is added, it tends to reduce the amplitude of the medieval climate anomaly. You still see the little ice age appearing. That does appear to be much more of a genuine global event, whereas what we think of as the medieval climate anomaly was certainly a real event, but it was more transient, didn't occur all places at all times at the same time. And in fact, when it was warm in one place, it was cooler in another. So, but at the time when these papers were written, there was still a lot of controversy about the role of tree rings. That was when it was really hot. And of course, it was leading up to, not long after that, we ran into the whole climate gate thing and everything as well. So, yeah, that's what I understand.
Thanks. And you might have asked one more question.
Sure.
I'm looking at the graph. I'm looking at the page that has the Pacific Decadal Oscillation, the ENSO index, the Atlantic Oscillation Index. My question is, so if I heard you correctly, when you were explaining the Pacific Decadal Oscillation, did you say that there is a hypothesized trend? If you look at, obviously I see the recent temperature increase, ocean temperature increase. I guess what I just necessarily don't see real clearly is a corresponding increase of the PDO. Is that something that you stress to your students? Because I'm just trying to.
What I do is, again, is why we do this. Part of the reason I'm getting them to do this is just to look, to observe, record, analyze, like a scientific method, as it were. And if you look at the El Nino index and the PDO index, there is clearly some correlation. It doesn't mean causation. And I know just from my reading is that it sort of comes and goes. In other words, it would be nice if there was a definite relationship between one and the other. The El Nino is clearly the more energy intensive of the two. And so the thought is that there could be a link that the El Nino drives at some level the PDO. But I haven't read that. What I've read is it's an idea, and some people think it happens, but it's not certain yet. And again, this is one of the wonderful things from my perspective, is that this is such a multidisciplinary subject that each of us can't be an expert in all fields. So if anybody's an expert in the audience, as it were, please chime in and help everybody to understand that better. But that is what I understand.
Right. One of the things that I find, I teach, I don't know where you are in terms of where you are in your academic institution, but I teach at a small liberal arts college where science isn't most of the students are coming in with fairly weak science backgrounds, and one of the things I find is explaining these things. There's so many concepts that tie into them that it becomes a bit difficult.
I agree. I'm at the University of Richmond, which is a liberal arts college, although we do have a fairly strong program, but the students I teach typically have, I would say half of them have a science background and half of them don't, and there's not a lot of difference between them. So I tend to assume total ignorance. I always think it's good working with students and faculty to assume total ignorance when you start, and I'm rarely disappointed. I have had a lot of good feedback from these modules from students and faculty who use them in class. Because, again, they're not prescribed. It's information that you can use as you want. It's one of the reasons, again, I just didn't put PDFs up. I wanted you to get the real data to play with as you want. And quite often faculty who've used this take it in a completely different direction, getting students to look at specific periods of time or analyzing data in a different way. So I hope that people who use this don't just run through my idea of what it might be, but explore it themselves and use it and expand it and extend it for their own purposes.
Right. And do you mind if I ask one final question about the hurricanes, about the Atlantic Basin hurricanes figure?
There we go.
I give an assignment to my students that looks at a paper that has some of that data in it, and I was never aware, looking at that data, I see relative to the 1970s, 1980s, early 1990s, the number of Category 3 and Category 4 storms in the last, say, 15, 20 years has gone up. But looking prior to that, 1940 through, say, 1960, 1965, it seems that there were a sort of an equal number of significantly strong storms back then. And I was just wondering if you had any insight as to why that might be.
Well, I mean, if you're looking at the American multi-decadal, what I've understood is that looking at the AMO index, if you're looking at, let me just take this through, between 1940s, 1950s, and 1960s, we're in the positive phase. And during that time, it sort of corresponds over here to, it's not a precise, it's not every year, is it, but the frequency of it. And so I try and bring this out in the questions, asking how many hurricanes of intense hurricanes were there during that period of time. And if you count the number of intense hurricanes over this period of time and the number of intense hurricanes in this period of time, and compare to the number of intense hurricanes in the intervening period, it correlates reasonably well with the changes in the AMO index, which of course isn't surprising because when the surface ocean temperature is higher, then you're going to spawn more intuitively in most years. Of course, hurricanes are such ephemeral things; they depend on so many factors coming together. But still, it's one factor and a critical factor which will tend to give you more when the ocean is hotter.
Right. Thank you very much. That was a wonderful presentation.
Thank you.
Okay, David, we have approximately 3 minutes left. Do you want to take one more question? I think Virginie Rolland, and I don't know if that's supposed to be Virginia or Virginie. Do you have a question?
Yes, it is Virginie. I'm from France, so my name is biased.
Great. Go ahead. Welcome. Go ahead with the question, please.
So I know that those exercises are for undergraduate students, but I think they could be useful for graduate students too. I taught a seminar last semester, and I tried to focus on the impact of climate change on animal populations and plants as well. But I had to explain how things work in terms of natural variability and human-caused variability in climate. And I use different papers to discuss, and I see that there are some graphs in your exercises with references, but some of them don't have a name. So where do the data come from? Should we cite your name, or are the references in the PDF?
I believe, or I made an error, that all on the original spreadsheets that this data comes from, which are attached to the exercise, all the references should be there for the original data. If some is missing, then I made an error, and I need to get that corrected. So it's one of the important points for me, is that students know how to get back to that original data. So it may not always be there on the PDFs, on these graphs, but if you go back to the Excel spreadsheets that they come from, you should find it there. And if not, please let me know. I'll double check, but please let me know, because I do intend that to be there. And I can't be 100% confident I haven't missed one, but please let me know if I have missed it, and I'll fix it.
Okay, well, I haven't yet, so don't worry. I will check, and they're probably there. I had another question. Since my focus is not on the climate change causes, but I still need to introduce that to the students, what do you think would be the most compelling exercise for them?
The most compelling exercise for, I missed the first part, I'm sorry, I apologize. For which students?
What do you think would be the most compelling exercise to convince the students that climate change is not, I mean, a part of it is natural, but most of it is because of humans? What would be the most compelling exercise?
It's probably a combination of the first exercise, which just looks at how temperatures change in the ocean and the atmosphere over the last century, and then compare that with the the amount of energy coming from the sun. I mean, that comes from many of the exercises, but particularly looking at Milankovitch cyclicity, where we can see that the amount of radiation coming from the sun has been at the critical level of 65 degrees north, has been decreasing. this is to do with the tilt. I mean, here's the picture. Here's to do with the tilt of the Earth, so that we're not getting closer or further away. So the total amount of radiation reaching the Earth isn't changing, but it is distributing that energy differently over the surface of the Earth. And the way it's changing at the moment, which is the Earth's tilt is decreasing slightly, should lead to cooling. And it's not. We're seeing increasing levels. And then also looking at the intensity of sunspot intensity over the last 15, 20 years, where although up to 1980 it was increasing, since then it's been starting to decrease. Which is why when you look at a lot of climate skeptic blogs, they'll show this wonderful correlation between global temperature and sunspot activity, but of course it stops at 1980. And if you were to continue that on after 1980, you'd see this large gap appearing between temperature, which continues to rise at the same rate, and the sunspot activity, which falls off rapidly. Of course, you don't show it because it destroys their argument.
Okay, thank you.
David, we are out of time. I will briefly put up the next webinar schedule, but you can find that on the CAMEL homepage. And we encourage you to sign up for the other webinars, and the recorded one from today will be posted. Give us a couple of days to get it posted, but in case you miss part of it, you can find it there.
Can I just say, anybody who follow up with me,
go ahead, David.
I'm assuming everybody has my email address, because if anybody has a question they wanted to ask and weren't able to, please send me an email. I'll be very happy to work with you and try and help in any way I can, especially if there are any constructive criticisms. That's the most useful thing to have, so send them to me.
Thank you very much. That was very helpful.
You're very welcome.
Yes, thank you very much.
Thank you.